So as we were saying, we're going to be talking about the spontaneity of redox reactions. Remember that a galvanic or a voltaic cell is a cell that converts chemical energy to electrical energy through a spontaneous oxidation and reduction reaction. So before we can address the spontaneity of such a reaction, there's a few things that we need to talk about. First of all, we need to remind you that an electron has a charge of 1.6 times 10 to the negative 19th coulombs. Now that value is actually negative because, of course, the charge of an electron is negative, but the magnitude of that charge is 1.6 times 10 to the negative 19th coulombs. Therefore, if you had a mole of electrons, the charge on 1 mole of electrons would be 1.6 times 10 to the negative 19th coulombs times the Avogadro's number of 6.022 times 10 to the 23rd. So if we round that value off, we get about 96,500 coulombs of charge for every 1 mole of electrons. This is known as the Faraday's constant and is given the symbol F. Now, what are we going to do with this value of F? Well, E naught of the cell, excuse me, not E naught, but E of the cell, right? The voltage or EMF of the cell is the number of joules of work per charge that the cell can do. That voltage or EMF is the maximum voltage that the cell can acquire. The voltage can't be any higher. So it's the maximum number of joules per coulomb or the maximum amount of work that the cell can do per coulomb of charge. That maximum amount of work, or W max, is equal to the number of coulombs of charge, C, times the potential of the cell. So, coulombs of charge turns out to be equal to the number of moles of electrons that pass through the cell through the redox process times the Faraday's constant. If we replace coulombs of charge in the equation above with coulombs of charge, which is equal to N times F, so if we replace coulombs of charge with N times F, we get an equation that looks like this. So the maximum amount of work that the cell needs to do in order to move charge through the cell is equal to minus N, which is the number of moles of electrons, times the Faraday's constant, times E of the cell. Now remember, my friends, these reactions are spontaneous. And everybody here knows that if the Gibbs free energy, or the change in the Gibbs free energy, is negative, a process is spontaneous. Remember, the change in the Gibbs free energy represents the energy that is available to do work. So, if there is energy available to do work, a process will be spontaneous. If there's not energy to do work, the process will be not spontaneous. It turns out that delta G and W max, the work required, the maximum amount of work required to move the charges through the cell, are basically one and the same. And so delta G is equal to minus NFE of the cell. So as we said, delta G is equal to negative NFE of the cell. This equation can be applied to, obviously, the delta G under the standard state conditions. And again, it is also equal to minus NFE of the cell, but it is E of the cell measured under the standard state conditions. And again, as you recall, is the number of moles of electrons in the redox reaction. And F, the Faraday's constant, is 96,500 joules per volt mole, which is the same thing as 96,500 coulombs per mole. So, in a previous chapter, we learned that delta G naught was equal to minus RT, the natural log of K. And we know that K can help us determine whether the reaction favors the forward reaction or the reverse reaction in an equilibrium situation. Therefore, since delta G naught is related to K, we also know that delta G naught tells us really the same thing. We also know that delta G naught is also equal to minus NF E naught of the cell. So we can take the equation as it is, remove the delta G naught, rearrange the equation, and come up with an equation like this, where E naught of the cell is equal to R times T divided by NF times the natural log of K. And we see, just like delta G naught, E naught of the cell is telling us the same thing as K does, because it's related to K. It's telling us whether or not the forward or reverse reactions of the redox reaction is spontaneous, or excuse me, not spontaneous, but is favored. Is the forward reaction favored or is the reverse reaction favored? So let's say that we decide to have the reaction occur at a constant temperature of 298 Kelvin. Well, we know R is a constant, that's the ideal gas law constant. And F is the constant, that's the Faraday's constant, which you can see up above. The temperature is set at 298 Kelvin, and if we do that, if we plug in those numbers, we will see that the joules cancel with joules, the Kelvin cancels with the Kelvin, the moles cancel with moles, and our equation turns into this. So this equation says that E naught of the cell is equal to 0.0257 volts over N times the natural log of K. This is only true if the reaction is taking place at 298 Kelvin. If it's not taking place at 298 Kelvin, which is 25 degrees Celsius, then the former equation, the equation up above, is the equation that you would use. If you don't like the natural log version, well, guess what? We have a base 10 log version. So you see, natural log version, base 10 log version. You choose. And one or both of these equations may be in your packet. Make sure you check. This little diagram here shows us the relationship between delta G naught, E naught of the cell, and K. So we can see that there is a relationship between all three of these things. We can see with the arrows that are going in between how they equate to each other. But we know that all three of these things are telling us the same thing. They tell us whether or not the reverse reaction is favored or whether or not the forward reaction is favored. This little chart shows how it all works out. When K is much, much greater than 1, our delta G naught is negative, and our E naught of the cell will be positive. If our E naught of the cell is positive, our K is greater than 1, and our delta G naught is negative, it favors the formation of the products. If K is equal to 0, then both the delta G naught and the E naught of the cell are 0, and neither the reactants nor the products are favored over the other. And of course, if our K is less than 1, then our delta G naught is positive, our E naught of the cell is negative, and that tells us that it favors the formation of the reactants, and therefore the reverse reaction is favored over the forward reaction. So here's a problem that we're going to try. It says, what's the equilibrium constant for the following reaction at 25 degrees Celsius? So we want the value of K, the K sub C, I believe in this case. We know that E naught of the cell is 0.0257 volts over N times the natural log of K. And this is true because we know it's happening at 25 degrees Celsius. So in order to solve this problem, we're going to have to break this down into the two half reactions and figure out what's being oxidized and what's being reduced. The oxidation process is the fact that our two silver atoms is being oxidized to form two silver ions, releasing two electrons. And of course, therefore, our reduction process is the fact that the Fe2 plus is gaining those two electrons to form Fe. So we have 2 moles of electrons being formed in the oxidation process, and we have 2 moles of electrons being absorbed in the reduction process. That is the same 2 moles, okay? So the 2 moles of electrons being lost are the 2 moles of electrons that are being gained. Therefore, the value of N for our equation up above is 2, not 4. We know that E naught of our particular cell is going to be equal to what happens at the cathode in terms of its E naught minus what happens at the anode in terms of its E naught. We can look up those values in our textbook, and we would determine that the reduction potential at the cathode minus the reduction potential at the anode looks like this. It's a negative 0.44 volts minus 0.80 volts. We get an E naught of a negative 1.24 volts. Now, of course, if you look at the chart that we looked at before, you would see that because if our E naught of the cell is negative, that this reaction does not favor the forward reaction and actually favors the reverse reaction. But we're going to use these values that we've determined to actually still find the value of K and see if we can confirm that this is true. So if we rearrange the equation up above, K is equal to E, that EXP stands for E, raised to the E naught of the cell times N over 0.0257 volts. That is the power to which E is raised to. So if we plug in E naught of the cell, if we plug in the value of N, and we turn the crank, we get the value of K as being 1.23 times 10 to the negative 42nd. And we can see that it is a number that is much, much smaller than 1. Therefore, we can see that the reverse reaction is favored over the forward reaction. Reactants are favored over products. And we would see that E naught of the cell, which is negative, is telling us the exact same thing. Okay, that's it for this video. Next video will be in just a few minutes.